right, welcome back to CS50. This is the end of week 3. Nothing stupid to start off with today on the overhead. Instead, I need 8 of you, if you would be so brave. Yes, 1, come on. OK, number 2, come on up. Don't look up. No one's looking up in this area. 3, OK, come on up. Again, you must be comfortable on camera. You 2, come on. OK, wait, let's see. 1, 2, 3, 4, 5. You 3 in front here. How about? Yeah. We'll do some other awkward things in the future, I promise. OK. So here we go. If you could line up in that order up here on stage. Uh-oh. Oh, perfect. Perfect. OK, so if you guys could make yourselves look like that. The first moment of awkwardness here is just to remind you where we left off last time, and that was the goal. Among the goals on Monday was to actually search numbers. And we had a wonderful demonstration that worked perfectly, whereby Edward found the numbers in question immediately. But at least the second time around, in theory, he was able to assume that the bottommost array was actually sorted. So today we asked this question, how do you go about sorting those numbers? And for this now, we need the 9th volunteer. There was yes, in the pink shirt there. Come on down. So this gentleman here will be in charge of the sorting demonstration. So we have 8 numbers. And if you would, as this gentleman comes down, think to yourself, you've got 8 humans here, each of which is representing an integer. How would you, the human, go about sorting these folks? And let's see if yours actually coincides with Adam's approach. So Adam, your goal here is simply to tell these 8 what to do and sort them from smallest on the left to largest on the right.
All right. Will you please switch? Will you switch with him? Will you go to the end, please?
There you go.
Oh. And then will you come in between these 2?
Well, a round of applause. Absolutely. That was fantastic. OK, so what was Adam's approach? Can someone put into words what he just did? What is the algorithm? How would you specify this? Not so many volunteers now. Yeah? OK.
All right, determine the least number and put that in the first index, and then repeat recursively for a smaller set.
OK, good. So look for the least, look for the smallest number, pull that person out and tell them go to the beginning. And then repeat, recursively, so to speak, do the same thing again, but with a problem that is ever so slightly smaller, n minus 1 instead of n. And in fact, we got to the end result. What was your actual approach?
It was basically what he said, except I also tried to look to make sure not to change anyone that was in the correct position already.
OK, good. So we had a little optimization heuristic, perhaps, whereby if someone was already in the right position, we didn't move them at all, thereby not wasting any cycles. OK, so let's see if we can't slap both a label on this for the sake of discussion, but then also make some claim as to the efficiency of what Adam just did. So let's see here. Could you go back to the order you were just in? OK, and so we pretty much just did what this gentleman said. We selected, so to speak, the smallest element. Is it this person? Is it this person? Is it this person? Aha, we found it. And notice the one difference here. So the human, Adam, might have immediately gone for, obviously you're number 1, you go here. But remember, a computer is not going to be able to sort of omnisciently be able to know who is the smallest and where they are. Because if you think about how you would represent these 8 humans, I mean, what data structure, as we'll call it, would you use these days in C? So you'd use an array, much like you might have had a list in Scratch. But an array, even though it allows you random access, where you can jump randomly to any one location just by indexing into the array numerically by way of those square brackets, that doesn't necessarily mean a priori that you know where to look. So for instance, your name is? Gabrielle. So Adam didn't necessarily know that Gabrielle was in index location 0, 1, 2, 3, 4. He only knew that presumably because as a human, he very quickly scanned the list. But much like a computer, did he have to start somewhere? So start at the left, move to the right, and then finally he saw Gabrielle. And then just to push a little harder here, once you found Gabrielle, did you know this was the smallest element?
I did.
OK, you did. Why?
Because I had already seen all the other elements.
OK, good. So there's at least some knowledge in advance here as to what the numbers are, so he at least was able to optimize there. But in the worst case, if you didn't have this little cheat sheet that's 20 feet high over here, what would you have had to do to find that smallest element?
Check the last 3.
OK, good. So check the last element. So maximally finding Gabrielle, or more generally finding the smallest element, would take, from the audience, how many steps? OK, so n steps, right? You start here, you check. 4. OK, 4 is actually the smallest element I've seen. But let me keep looking. Oh, 2 is even better. Let's forget about, what was her name? Preya. Let's forget about Preya, because we've just now found Juliana, whose number is smaller. So now think about how you would implement this. I just need to keep around, it seems, a variable, I or n or whatever, that keeps track of maybe what the smallest value is, or at least where it is. So index location 1. And then I keep going, keep going, keep going. Finally, I get to Gabrielle, and I update my variable because I found something better than Juliana. And now I keep going, and then I get to these guys and realize that was a waste of time because I've already found the smallest element. So I pull Gabrielle out. And then what did you tell her to do exactly?
Switch with Priya, I believe.
Excellent. OK, good. So notice, and if you could implement this in reality. So we've switched them. And this was actually pretty smart, because what would another approach have been to make room for Gabrielle down here? Yeah. OK, so we could make another array. And we'll see in time how you can create arrays in advance that are as big as you'd like them, subject to RAM constraints. So we could just kind of make a bunch of blank space, then start filling in the holes. What would another approach be, as opposed to just having these two swap? So we could shift people, right? If you could go back to your original locations for just a second. Another very reasonable approach would have been to say, OK, come on out of the line, if you would. You guys make room. She's got to go into the front of the list. But that's another 1, 2, 3, 4 steps just to make room now for Gabrielle. So we have a couple of options here, right? It's clearly, in a program, it's going to take us n steps to at least find Gabrielle, or more generally, the smallest number. But even then, after that, there's some clever decisions we can make, like, as Adam did, swapping the two instead of foolishly, though correctly, shifting everyone down. So let's now ask the question. If this algorithm is essentially defined as selecting the smallest person, moving them immediately to the front of the list, and then repeating, as this gentleman said, how many steps maximally is this algorithm going to take to sort everyone? So it's not as bad as n factorial, thankfully, because that would actually get really slow really fast.
Like a little less than n squared.
Oh, OK. Say again?
Like a little less than n squared.
Yeah, it's actually a little less than n squared. Well, why is that? Well, let's see. If I take n steps initially, I take n steps and I get here. But now what do I have to do? I essentially have to repeat, but I can slightly optimize, right? Because I already put Gabrielle in the right place, so I don't have to look at her number again. So now I have n minus 1 steps. And then on the next iteration, n minus 2 steps. Then n minus 3, then n minus 4, dot, dot, dot. So that begs the question in the end, what is n plus n minus 1 plus n minus 2 plus dot, dot, dot down to 1 or down to 0? And what is that? Anyone remember the little cheat sheet at the back of your high school math book? Yeah, so it's n times n plus 1 all over 2, right, which is roughly what? N squared. So let me part the river here for just one moment. Sorry, we'll get you some cough medicine shortly. So that series, n plus n minus 1. I promise not to do too much math while you guys are standing here. Plus, whoops, not n plus 1, n minus 1 plus n minus 2 plus dot, dot, dot plus all the way down to the very last step. You may recall that this generalizes as n times n plus 1 over 2. What does that equal? Well, that's n squared plus n over 2. And now is when we apparently have a way of expressing the running time of this algorithm. And we talked on Monday about big O and omega and what those actually mean. So what's the worst case running time of this algorithm? So it feels like it's big O of this. So big O of this thing here. But one of the rules of thumb when it comes to talking about the running time of an algorithm, mathematically or formally like this, is when you start talking about really big values of n, adding another little n like this doesn't really matter. You start to care more about the degree, the member in the formula that has the highest exponent, for instance, because if n is not just 8, but n is a billion, well, n squared, a billion squared, that's a really big damn number. Plus 1 more billion, not so material. And so when we talk about big O notation, we tend to get rid of the smaller terms. And this divided by 2, I mean, that's really not so interesting either, that we actually actually only did half as many steps. And the motivation conceptually for this is essentially this idea. When I started counting everyone linearly in the lecture hall the other day, 1, 2, 3, we immediately improved on that. That was a big O of n algorithm, but I immediately started doing 2, 4, 6, 8, 10. So that's like an n over 2 algorithm. And mathematically, n is slower than n over 2, because I'm doing twice as many steps in the first version and half as many steps in the second. But you know what? If I wait 12 months, 18 months, Intel is going to come out with a faster CPU that tends historically to be twice as fast. And so over the course of a year, my algorithm, naive though it was, automatically gets twice as fast. But that's not interesting. We need to be able to abstract away from the running time of me, the human, the speed of me, the human, or the speed of the machine implementing these algorithms so that we can say something interesting about the performance of algorithms independent of however many gigahertz happens to be in vogue at the moment. So with that said, the big O running time of this algorithm, we would say, is just big O of n squared. Now, what about in the best case? If you guys could realign, as you were a moment ago. This is not the best case, but what would the best case scenario be for Adam upon arriving on stage?
Everyone's already in the right place.
OK, so everyone's already in the right place. So if you could quickly sort yourselves, just from 1 through 8. So now Adam has just arrived on stage. He is handed this array, say with no other knowledge in advance. If he applies that same algorithm of looking for the smallest element, putting him or her at the front, then repeating for the n-1 remaining elements, then repeating recursively, how many steps is the algorithm going to take this time? So it's actually not 8. At least as we've described it here, it's the same number, because what does he not know upon each iteration of this, if we implement exactly the same algorithm?
I'm still not sure if one's the smallest element, so I have to still check all the way down.
Exactly. So again, ignore the cheat sheet that's up here. If Adam's the computer that's been handed this array of 8 numbers, that's wonderful that they're sorted. But his algorithm is not designed, as we've just described it, to really take that into account, because he's still going to start at the left, and he's going to realize, oh, wow, this is a really small number. I'm going to remember this one. Bigger, 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 bigger. Damn, I just wasted 7 steps, and yet I had the winner at the very beginning. OK, so I'm going to leave her where she is. Now let me repeat for the remaining elements. All right? Oh, here is the small number, 2. I'll remember this. Bigger, bigger, bigger. I've wasted more time. But I'm going to keep wasting time, because at least with this algorithm, defined as iteratively or recursively selecting the smallest element and plopping them at the beginning, there's no cognizance of whether or not the list is already sorted. Now, you might think, well, this is just stupid now, right? Just keep track of whether or not you've seen smaller numbers before, and that's fine. But that's a different algorithm then, right? We need more memory for that, or we need a different set of steps. So let's try one other approach at least here. Could you guys reshuffle in this order? And this is really random. It doesn't matter what they reset to, but at least this gets it done quickly. So what might another approach be? And let's tell Adam this time what to do rather than leaving it to him. How else could we go about sorting these 8 people? Bubble sort. What a wonderful lead-in. OK, well, what does that mean? Well, let's think about another very simple approach. This is a really kind of overwhelming problem. 8 numbers. I'm the program. This is a lot of work to do. Let me keep it simple. And let me start at the left. So these 2 here are clearly out of order. 4 is bigger than 2, but 2 should be to the left of 4. So you know what? Let me just try a very simple algorithm of swapping these 2 volunteers. So we swap them. That takes 1 step, or maybe 3 steps if you think back to our swap operation, but a fixed number of steps, a constant number of steps. And that's OK. We're more worried about recurring costs. All right? So now I compare 4 and 6. So these 2 are actually in pretty good shape. I'm going to leave them alone. 6 and 8, they're good. 8 and 1, let me do a swap. But again, I'm not backtracking. I'm still making forward progress. 8 and 3, got to swap these 2. 8 and 7, going to swap these 2. And then 8 and 5, going to swap these 2. Done, right? All right, so obviously not, right? The list is not sorted, so I've taken n steps here, done some swaps in the middle, but any swaps were just constant time anyway. It's always the same number of steps to move 2 humans or to swap 2 ints. So what do I do now? Well, let me try repeating. 2 and 4? No. 4 and 6? No. 6 and 1. And now notice what's happening to Gabrielle this time. Go ahead and swap. So notice, and we can slap the label that's already been applied to it on this algorithm, the smallest number seems to be bubbling her way up to this end of the list. And meanwhile, 8 has already bubbled his way up to the end of the list. So this algorithm is, in fact, generally called bubble sort. It is just as correct as the previous one that Adam proposed, which was generally called selection sort. So that begs the question, is one better than the other? Well, how many steps is bubble sort going to take? So it's also n squared. Now, why is that? Well, let's see. Every time I want a move from left to right, I'm looking at 8 elements and maybe doing some constant number of swaps. So some product of n am I doing through each iteration. But in the worst case, who is where in this scenario? So in the worst case, maybe Gabrielle is all the way over here, and this gentleman, Ravi, is all the way over there. So that then begs the question, if on each iteration someone like Ravi or Gabrielle only bubble up one place to the left or one place to the right, how many times am I going to have to repeat this process to pull Ravi all the way that way or Gabrielle all the way this way? Well, another n times, or n minus 1. So I have to do n things n times, and that one conceptually is perhaps even easier to wrap one's mind around. It's big O of n squared. Now, I think we've had you up here for an awkwardly long enough moment. A big round of applause, if we could, for Adam and these guys. Thank you. Little souvenir. And if you want, our paperwork awaits. Thank you. So let's see. No, we don't need to do it every time. We have you for life now. All right. So let me go ahead and show exactly what this means for something to be taking n squared time, because we'll actually see that n squared, though very simply defined, and that was actually pretty simple to implement. If you think about it, I've got a for loop, then maybe another for loop. So I can pretty relatively easily translate what we just did with Adam and team into code. Well, let's see if we can't visualize it as well. So this is a link that we have on the course's website under lectures. And it's just a really nice Java applet, a program someone happened to write in Java, works in a web browser that helps us visualize some of these algorithms. If I go down here to this dropdown, if you want to play along at home, and I go choose bubble sort, array type random, sure, it's just going to populate it randomly. And this delay is just going to control the speed of this demonstration. I'm going to make it 10 milliseconds or whatever this is. And now I'm going to go ahead and click Start. What we have here is a larger input set. So each of these bars represents a number, or human. The taller the bar, the bigger the number. The shorter the bar, the shorter the number, the smaller the number. So Gabrielle would be the small bar up there, number 1, and Ravi would be one of the larger bars at right. That's the analog here. So what's happening in red from left to right is that this program is implementing bubble sort. It's comparing pairs or neighbors of elements, and if they happen to be out of order, it swaps those two, but then forges ahead to do it again to the next pair of neighbors. And what you can see perhaps more easily, since this is a longer demonstration, that bigger numbers are in fact bubbling up, albeit slowly, and smaller numbers are bubbling their way down. Now, this is only what? That looks like 30 or 40 bars total. So n is not very large. And granted, we fixed the speed of this thing, but it's already getting kind of boring. So n squared does not scale particularly well. Sorting elements with even more than 40 elements, or whatever is up here, definitely takes a while. And let's see then if selection sort does a little better. So I'm going to go ahead and choose selection sort, as it's called. I'm going to go ahead and click Start again. And now notice less seems to be happening, but that's because this algorithm is swapping bars as far to the left as possible on each iteration. So what's getting highlighted in red is the then smallest element that's been discovered, say by Adam, and then it's being moved all the way to the left. So what's a little neat about this algorithm is that you can actually see the progress, and that definitely happened more quickly. Right? If we ran it again, or you actually timed it, I mean, I'm still talking, and yet this thing is done. Selection sort seems to be faster. And that's because what I've crossed off here for formality's sake definitely has real-world implications. So n squared is slower than n squared divided by 2, for instance. But realize once we start talking about really large data sets, the number of Facebook users out there, or the number of web pages that Google indexes, this is when things like n squared and these design decisions really start to hurt potentially, because they take yet more time than you might necessarily have patience for. So let's see if we can express this in a way that is more easily translated to code. So here's bubble sort, pseudocode for it. You can write this in any number of ways, but the algorithm essentially boiled down to repeat the following n times. For each of the elements in the array, if I, as we'll call it iteratively, and its neighbor are out of order, swap them. So this is, again, another lesson in pseudocode, what it means to communicate your ideas without getting bogged down in uninteresting minutiae like syntax specific to C or any other language. But with the expression of pseudocode here, you can see perhaps more clearly the actual running time. You can see in the very first line there, repeat n times. You have an explicit directive that the following is going to take n steps. But beneath that, it says for each element I. Well, how many elements are there? There's n elements in the array, so a for each loop is going to induce another n steps. So you can immediately see in the pseudocode alone that this algorithm is apparently going to take n times n steps to actually get the job done. Now, bubble sort actually allows for more optimization, though. So when we had our 8 volunteers up here, we, for the sake of selection sort, told them to get into proper order. And then we asked the question, how long would it take to sort these elements using selection sort in the best case? But we didn't ask that in bubble sort's case. So if in bubble sort's case you have 8 humans here from 1 on up to 8 already sorted, how many steps is this algorithm going to take as written? So I'm hearing a few answers, among which are n squared, n, I heard 7. But it is, in fact, again, just look at the code, if you will. Do the following n times for each of the elements, so n more things. If I and its neighbor are out of order, swap them, no matter what. This implementation of bubble sort is just blindly telling you to do the following n times, n times. This algorithm takes n squared steps. So if Adam had come on stage, realized, had been handed an array of 8 people, all of whom were sorted already, doesn't matter. He's going to very blindly compare again and again for a total of n squared steps all of the humans in that row, and then eventually he's going to stop, because what's neat about this algorithm, at least, is that because you are doing it n times, no matter what, it will have worked by the end. But there's clearly an opportunity for optimization here. So bubble sort right now, let's slap some numbers on these just to have sort of a list, and then see if we can't do better. So bubble sort. So bubble sort thus far, it seems to be in big O of n squared. Selection sort seems to be also in O of n squared. But we also said it also is in omega of n squared, because, again, you just keep going through and going through, selecting the then smallest element, but you don't know in advance that you found the smallest element until you've checked. So is omega of bubble sort better in this case? So no. So can we do better? How would you optimize this algorithm? How would you, after receiving some feedback from your TF, go back to the drawing board and just add a couple lines of code to fix this? Yeah? Yeah. OK, so keep track of how many switches you've made by way of a variable. So initialize some counter variable in there, initialize it to 0, and then as you iterate over all of the elements, if you actually execute this if condition and swap elements, what should you do with this variable? The little plus plus, right? Or it could be a Boolean. It could just be a Boolean that says true, I have swapped something. Because then when I get to the end of the list and I meet Ravi, who's been here the whole time because he's already sorted and he's number 8, what do I then check before deciding whether or not to repeat this algorithm? Right, so if my variable equals 0, don't waste your time going back to the beginning and repeating this algorithm. Instead, do something like if variable equals 0, and new line, break. So break is a syntax you might have seen in section or some past examples. You can forcibly exit a loop simply by executing the statement break, semicolon. And so that would be the easiest way of translating that little optimization to code here. So what are the returns? What then is the best case running time of bubble sort? Yeah, it's just n. And that's cool. Right? So that was easy just by adding 2 lines of code. And again, testament to this idea of putting up a little more effort and thought and intellect into the design of an algorithm. Can you significantly chip away at the running time, which, as we saw on that big chart the other day, something that's linear is much, much better as n gets really, really large than something that's quadratic or polynomial. So this is already a good thing, but it still feels pretty slow. So is there another approach altogether? Well, I'll wave my hands at some more pseudocode here, since one could write this in any number of ways. And this just expresses what Adam and our volunteers already put forth to us. But it turns out that this trick from Monday, this capability of a function's calling itself, is actually a really powerful thing. So there exists this other algorithm called merge sort. And as the name implies, it boils down to taking an array, or taking a list more generally, sorting half of it, sorting the other half, and then merging the results. And voila, you then have a perfectly sorted list. Well, how does this work? Well, this is it. So this is the pseudocode for merge sort. It says on input of n elements, so in the form of an array, first you do a sanity check. If you've got fewer than 2 elements, there's no work to be done, return. And if you can recall the lingo from Monday, that represents our... So that's the base case that actually prevents this thing from devolving into a really bad infinite loop, after which bad things, segmentation faults, and all of that happen. So else, if you do have enough elements to actually do interesting work on, what should you do? So sort the left half of elements, sort the right half of elements, then merge the sorted halves. Well, what does this mean exactly? Well, if I have a list of 8 numbers, and I then take the 4 numbers on the left and the 4 numbers on the right, how do I go about sorting the left half of those elements? What would you do? Right, I've got 8 volunteers here who we have dismissed, but pretend there's 4 people here, 4 people there. I have to divide the list into 2, so here's the 4 people I need to sort. How can I sort half a list? How about in back? Cut it into 3/4. OK, so I could cut it in half again, again, and again. OK, so finally I get down to Gabrielle or any of our volunteers, because I've cut my list of 8 into 4, into 2, into 1. What do I do now with Gabrielle or whoever I've found? Can't go back to your laptop now. You're on the hook. OK, true. But then what do I do once I keep cutting the list in half? Now I just have 8 people. What do I do with them? OK, I merge every 2. OK, so you're actually going, frankly, in this direction. But it seems like you're just kind of weaving a circular argument around me, right? I'm asking you how to sort n elements, and I've already cut them in half. You're telling me we'll just cut them in half again, and then cut them in half again. I feel like we're not actually getting to resolution here. Yeah?
Well, a single element is already sorted. And so when you get down to like 1 element, it's sorted. And then you would merge it with another element and put those 2 in order.
OK.
And then the pair next to that would be merged in order. And then those 2 pairs would be merged in order, and so on and so forth.
OK, good. So to summarize, maybe the magic here is not in this punting in lines, the second to bottom lines. Whenever I say sort left half and sort right half, I'm kind of just punting on that and saying, go sort these elements. Then the magic seems to be in the merging of sorted halves. Because if we kind of think through the logic that's been proposed, if I eventually get down to a list of 1, of size 1, just Gabrielle or just Ravi, there's actually a really neat feature of that situation, which is that Gabrielle, as a single number, is already sorted by nature. Similarly as Ravi or any of our 8 volunteers, already sorted if I try to sort just them. But then I apparently need to take a step back conceptually and say, OK, I've got a list of length 1. It's already sorted trivially, because that was really an uninteresting exercise. But now I have 2 lists, it sounds, of size 2. So I know this is going to happen, but I will say, let's take a 5-minute break, think about how we'll solve this, and then we'll reveal the answer after you've not actually thought about it. All right, so we are back. Here are, we'll do this one without humans, but here are the same numbers that our volunteers represented. The motivation here, to make sure the context is clear, is to do better than n squared. And even though the algorithms we've demonstrated both with humans and with computers up top hasn't taken terribly long, realize that we only had, again, 30 or 40 bars on the screen that were getting sorted, and even that was relatively slow. But the goal here will be to compare just how quickly or how much better we can do if, again, we inject a little more intelligence and start to deploy some more sophisticated techniques like this thing called recursion on Monday, which at the time, very uninteresting to implement factorial or sigma, the summation function with recursion, because we already had other ways of doing that. But as in this case, as we'll see, sometimes recursion lends itself to the expression of an algorithm that would just be much harder to express iteratively or with lots of loops and variables. So here's our algorithm, and let's see if we can apply this here. So here's our 8 elements. The first step is to, on input of n elements, if n is less than 2, return. Nope, n is actually 8, so I'm not going to return yet. So else I do the following. Sort the left half of elements. So somehow I need to do something with these guys here. No. With these guys here. So real world bugs as well. And then I'm going to move on to those, but not just yet. So I've called a function, essentially, sort left half of elements. So I need a way of sorting these 4 elements. What algorithm might I apply to these 4 elements? So I've got bubble sort, I've got selection sort, but feels like if I deploy one of the algorithms we've already dissected and analyzed and use it twice, that we're not really going to make a fundamentally important step forward. But you know what? We do have a new sorting algorithm, supposedly. We don't know if it works. We haven't seen how it works, but it is called merge sort. So let's take this leap of faith and sort the 4 elements on the left half with the same algorithm, merge sort. So you'll have a little bit of stories piling up in one's brain here as we do this recursively, but here we go. So I've just sorted, I need to sort the left half. That's these 4 elements, which means I'm invoking merge sort. N is now 4. Is 4 less than 2? No. So I do the else, sort left half of elements. Well, what does that mean? That means I now need to sort these elements here. OK, what does that mean? How do I sort 2 elements? Let's deploy merge sort. So call merge sort on a list of size 2. Is 2 less than 2? No. So I proceed to do the else construct yet again, sort the left half of elements. And here I go. I now sort the left half of elements, and voila, I seem already to be at the point where I have a list that's now of size 1. So is 1 less than 2? Yes, finally. So I return immediately. Now at this point in the story, I've got a list of size 1. What was the next step if you roll back in time now? So sort the right half in question at this moment in time, having called merge sort multiple times already, was sort the left half. Now I need to sort the right half. So I'm down at this point here. Sort 2 is trivial to sort because if n equals 1 is less than 2, I return. So now I'm at this point in the story. What do I do with 4 and 2? I've got 2 lists of size 1, and the goal now is to merge these sorted halves. How do I merge these sorted halves? Well, we can do this we can do it verbally. All right, here's a list, here's a list. I need to merge them somehow. All right, who's going to come first in the merged list? 2, obviously. So I'm going to make some extra space here. We'll call this, I need actually, in reality, extra memory for merge sort. So I'm just going to give myself an extra array, some blank space that I can start writing on. So here's 2 lists. I've already plucked off the 2. I advance to the next element in the list. There's nothing there. So who comes next? So 4. So now I'm at this point in the story, and I have a list of size 2 that's been sorted. Where did we leave off in the story now? So 6 and 8, right? Because this was the left half. But then this was the left half of the left half. We sorted him. Then we sorted the right half of the left half. That was easy. Then we merged the left half of the left half with the right half of the left half. And we got 2 and 4. So I realize this is actually a little confusing, but that's why we're actually doing a fairly small example here. 2 and 4 now are sorted. So who is their counterpart? Who is their right-hand side? That's these guys. So how do I sort the right half of this list? All right. I sort the left half of this list first. OK. Now I sort. That's already done because it's a list of size 1. Now I sort the right half of this list. That's already done. What do I do now? What's the third step in this sorting process? So I still need to merge them. We, the omniscient humans, can see they're already in order. But we, as the computer, don't know in advance until we actually look at them. So let's look at them. I've got a list of size 1, a list of size 1. Which one's going to come first when I merge the 2? Obviously, the 6. And then I advance this finger. The list was only size 1. There's nothing there. So now I merge the remaining elements 8. So I've got 6 and 8. At what point in the story am I? We've rolled back almost to the beginning. Right, so I sorted the left half, which was here. I sorted the right half, So the third step here and final step on the board is to merge the sorted halves. So now I'm going to do the same algorithm. And again, I tend to use my left and right finger when I need to represent a loop that has maybe two different indices, two different index variables. So how do I merge these two lists? Well, they're already sorted, so I don't have to compare all of the elements against every element. I just need to look at the front of them because I already know from my previous steps that I put the smallest elements there. So I now need to merge this list and this list. So here's the two smallest elements. I compare them. Is 2 less than 6? Yeah, it is. So let me put this into my empty space. Now I advance. OK, this time there's something there. So I don't just blindly take the 6. I now compare 4 against 6. Obviously, the 4 comes next. Now I advance. Now there's nothing to compare against. So I can just finish my loop over the 6 and over the 8. So at this point in the story, I've just finished which step? Sort left half. The very first time in this story that I said sort the left half was to sort these 4 elements. We finally completed that step. But notice what happened. It induced that simple goal of sorting the left half of elements, induced another call to merge sort, another call to merge sort, another call to merge sort, and then we merged the lists. But then we did the same thing. Another call to merge sort, another call to merge sort, another call to merge sort. Then we merged the lists. And we're not even done yet. So it actually feels like we're doing a lot of work here. But let's see if it pans out. Well, on the right-hand side, if that's the next step, I sort the right-hand side of the list. How do I do that? Sort the left half. All right, so that's these two guys. How do I do that? Sort the left half. All right, that's actually pretty easy. Done. It's a list of size 1. Now I sort the right half. Easy. It's a list of size 1. Done. Now the magic happens, but it's seemingly fairly simple. Merge them. All right, so how do I do that? I compare, and I'm going to plop down 1 first, then 3. These guys are now sorted. Where am I at the story? Now I sort the right half of the right half. So that means look at these two, chop it into left and right, do this, trivial, it's already sorted, do this, trivial, it's already sorted. Now again, the magical step of merging the two. And obviously, we get out 5 and 7. So now I have a list of size 2 that's sorted, another list of size 2 that's sorted, the left half and right halves, respectively, of the right half of the original. What's the last step? To merge the sorted halves. So 1 and 5, I compare. 1 comes first. Now I compare 3 and 5. 3 comes next. Now I'm out of numbers there. So 5 and 7 get plopped down. Am I done? Not quite. Merge sort boils down essentially to 3 lines of code. Sort left half, sort right half, and I've done that, and I've done that, and now the third and final step of merge sort is to merge those sorted halves. So what do? Well, I'm running out of board space, but I don't think it'll be all that enlightening to know that the numbers are now going to get merged as 1, 2, 3, 4. But how? Well, again, remember the 2 index variables. I've got 1 on the start of this list, 1 on this one. I compare the 2 fingers. 1 comes first, so I write down 1. Then I advance this finger. Now I compare 2 against 3. I put down 2, and I advance this finger. And the point of this little finger demonstration is to make clear that at no point is my left or right finger going backwards on the board. They're always making forward progress. In other words, every time I merge, I'm touching physically n elements. Or put another way, I'm touching every number once and only once, because once I've touched it, I advance and move forward again. I never double back. So in other words, from left to right, I seem to be conceptually always taking n steps in this direction. Every time I do merging, there's n steps involved because I'm touching every number once, but never going backwards. So that then begs the question on the other axis here, how many times did I go down in this list? How many times did I chop lists in half? Because if I'm doing something n times this way, hopefully I didn't chop the list n times this way. Otherwise, we've got an n squared algorithm, and this was all a waste of time. But how many times per week 0 can we take a list of size n, or a list of size 8, and divide it in half, in half, in half, and then bottom out with 1 element? So log base 2 of n. So even if you got lost in some of the details, that's certainly fine at first glance here. But just conceptually, what was I doing? Dividing the list in half, in half, in half, in half. And then I bottomed out with individual elements. How many times can you do that? Log n times. But every time I did that, the goal was to then merge all of the elements together, as we tried to do visually here. So I'm doing something log n times. And then each time I'm doing n merging steps, n moves of my fingers. So this algorithm feels like it should be big O of, and I'll write it here just for the sake of reference, big O of n times log n. And it's technically base 2, but just like we started scratching off constant numbers before in the context of big O, the base also means very little since it's just a constant value. You can convert one base in binary to any other constant value as well. So if I didn't do this depiction justice, let's just try to think about it more abstractly. If the problem at hand is to figure out what t of n is, the running time of an algorithm whose input is of size n, how can we actually compute its running time by looking at the pseudocode, essentially? So this is the algorithm. The last time we talked about pseudocode, we were able to slap big O of n squared on it just by looking at it. So let's see if we can't translate this to big O notation. All right, so this first line here, if n is less than 2, that's constant steps. So there's a 1 in there, something uninteresting. Clearly, the meaty part of this algorithm is down here in the else condition. So let's ask ourselves, what is the running time of this algorithm? Well, if you hand it n elements, we need to figure out t of n, which is just a fancy way of describing its running time. So what does that mean? Well, computing t of n means you first sort the left half of a list. So that's t of what? N over 2. Then you sort the right half. That's t of n over 2. So I don't know what the function is. I don't know what t is yet. But I know it's going to be the same thing, but with an input that's half as big. And then finally, how many steps does it take to merge sorted halves? Well, per my fingers moving slowly from left to right, that's some number of n steps, because every finger moves forward once, and then they eventually both stop. So we can express this, even without quite knowing where we're going yet, with an algorithm like this. T of n, the running time of an algorithm with handed n elements, is the same thing as sorting half of it, t of n over 2, plus half of it, t of n over 2, plus n steps. But you know, I'm kind of asking lots of questions, so maybe there's a constant factor in there. So here too, even in this context, can we say the merging takes linear time? I don't know exactly if this is 1 step to compare 2 elements, or maybe this is 2 steps. But again, these are constant values. Who cares? Let's just generalize it as big O of n. But now we've kind of turned in an answer that itself is recursive. What's the running time of this algorithm? Well, it's the running time of running the algorithm on half of itself and half of itself. Like, we haven't really made progress per se, but let's see if the numbers at least pan out. So how long does it take to sort, not 8, but we can do a little more interesting than that, 16 elements. But it's still a power of 2, just so that the math works out perfectly, even though in reality there'd be some rounding. So let's just plug these numbers into the formula. So the formula, again, is t of n equals t of n over 2 plus t of n over 2 plus some linear time. So let's do it. How long does it take to sort 16 elements? Well, t of 16 is t of 8 plus t of 8, or 2 times t of 8, plus 16 to do the merging. So sort the left half, sort the right half, plus the merging. Unfortunately, we've again gotten caught in a little circular argument here, because now the question is, what is t of 8 then? All right, well, t of 8 is the process of sorting the left half, which is now size 4, plus sorting the right half, which is also size 4. So t times 2 of t of 4 plus 8. All right, what is the answer to t of 4? Well, t of 4 is now this, 2 times t of 2 plus 4. What is t of 2? Well, t of 2 is 2 times t of 1. And hopefully we're now going to bottom out and not get stuck in this loop. T of 1 is just 0. Because how long does it take to sort 1 element? Well, no time. It's already sorted. That's when we returned immediately. So now we just have some high school arithmetic, a little substitution here. I now can fill in t of 1, then I can fill in t of 2, then and then it bobbles back up. So if we do out the math, and I've just flipped the numbers around so I can do the substitution from top to bottom, it looks like t of 16 is ultimately t of 2 times t of 8. But what is that? Well, that is just the answer to t of 8, which is apparently 24, if you go through the math. So long story short, t of 16 is 64 steps. Does this jive with the claim that the running time is big O of n times log n? Yeah, so 16, right? So if the running time here is n times log n, so an n is 16, that's 16 times log base 2 of 16, that's 4. So yeah, so 16 times 4, 32, 64. It is in fact 64 steps. So the claim ultimately is in fact correct, that merge sort takes 64 steps concretely with 16 elements, but more generally, n times log n. So what's the takeaway there? Like, who cares? Right? There's no point in memorizing that merge sort takes 64 steps or 64 seconds for inputs of size 16. But what would the n squared algorithm have been? How long would bubble sort have taken? How long would selection sort have taken? 16 squared, and that's, if you do the math, 256. And these are small inputs. Now I'm comparing 256 steps against 64 steps. Already the math is starting to work out in our favor. And if you think back to the slide where we had those graphs, when n really gets big, do these numbers really start to hurt? Well, it turns out there are other algorithms, to be fair, out there. So you will see things over time, whether in sections or in future CS classes, things called heap sort and insertion sort, quick sort, radix sort, shell sort. And as an aside, especially for one of the hacker editions, you might enjoy reading up on one or more of these. But n log n for now is about as good as we'll try to do. But let's just see exactly how good that is. All right, so here we have the second demo. This too is linked on the course's website. This is just another Java applet that someone very nicely put together. And each of these drop-downs is a whole bunch of sorting algorithms. So the world has had a lot of free time over the years to come up with algorithms like bozo sort and stooge sort and cocktail sort and a whole bunch of other silly ones. So apparently, if you come up with a clever algorithm, the fun part is you actually get to name it. But now we have from left to right selection sort, bubble sort, and merge sort. The question of the day was, can we do better than these initial algorithms, bubble sort and selection sort? And if so, who cares? Why does it really matter? What I'm about to do is click on each of these one right after the other, so that these things essentially run in lockstep. And let's see what it means for something to be in n log n as opposed to n squared. Apparently not much. There we go. Done. And with that, we'll see you Monday.